Alright, so g'day, my name's Thomas and thanks for coming to my presentation on developing an internationally competitive electric race car. I'm here representing the University of Canterbury motorsport team and I've been on the team for 4 years and each one of those years working on the electric vehicles. Last year I was the electric vehicle team leader and chief engineer as we took it to Australia at the end of the year. So, just a bit of an outline of my presentation. I'm going to talk about the Formula SAE competition and what that involves, a bit of an overview on our electric vehicles, including the attractive systems, the low voltage and control systems, and then some of the competition results that we've got from these vehicles. And then I'll briefly go over the 2019 team and then what's potentially in the works for the SAE team. Formula SAE is an engineering design competition which started in the US in 1980. It's a university competition that over 600 teams enter in worldwide, and each team has to design, build and then race a Formula-style single-seat race car. Across Europe it's got a parallel competition called Formula Student, which also works on, has the same idea. There are over 10 competitions held worldwide, and we enter in the Australasian competition, which is held in Melbourne in December at the end of each year. At the competition there is both static and dynamic events. The competition. So as I said, we enter in the Australasia competition, and the breakdown is a bit as follows. On the first day we arrive and begin the technical inspection of the vehicles. On day 2 the static events start, and then with the remainder of technical inspection. On day 3, that's the beginning of the dynamic events with acceleration and skid pad. And day 4 is autocross, and then the finale, endurance. Here is a bit of a breakdown on the points that are allocated for each event. As you can see, the endurance event is significantly the largest, with engineering design being the most heavily weighted static event. But before you can go on to racing, you must pass what could be the most stressful part of the competition for a team leader, and that's the technical inspection. First up is mechanical, where you're scrutinied against a panel of experts who judge your car upon its compliance with the Formula SAE rules. Then it's the tilt test, which the car is raised up to 45 and then 60 degrees, and must ensure that no fluids drip out at 45 degrees, and then at 60 degrees the car must be able to stay all on 4 wheels. Egress. Every driver that is to drive at competition must be able to egress from the car within 5 seconds. Brake test. You must prove that every driven wheel of the vehicle can lock up. After this, we then go on to electrical, in which it is a few more stages for electric vehicles than there are for combustion ones. First stage for EV scrutineering 1, you must prove that your car is capable of handling high voltage and all your components are rated within the rules. This also includes an inspection of your accumulator to prove that it's up to professional standards. Then it's EV scrutineering 2, in which the tractive system is livened, and you must prove that your vehicle is able to shut the car down given all the faults that are specified in the rules. Then it's the rain test, also another very stressful time. As you can see here, myself, the hat half on, and then Harry with his hands on his head. This was actually the first time we ever did a rain test, and you have to have your tractive system livened for 2 minutes under a shower of water, and then the insulation monitoring device must not trip, and I'll go on to that shortly. Static events. The biggest one of these is of course design, where you are broken into your sub-teams such as powertrain, electrical, suspension, aerodynamics and chassis, as well as things like management and things like ergonomics and safety. You then present your designs and your build process to a panel of expert industry judges who will judge you on your processes. Costing event is where you show how much your car costs. Essentially this comes down to who has the simplest building technique as well as the lowest number of parts. The business presentation is where teams must come up with an idea to make your car profitable. In the past, UCM has used an online racing syndicate in which you can race our vehicles in a virtual reality simulator. Dynamic events. Acceleration is a straight line drag over 75 metres, and of course it's time based. Skid pan is essentially a figure eight where you do multiple circuits of each loop before exiting, and it's also timed. Autocross, typically about 1 kilometre in length, and for autocross is 1 lap, and the fastest car to do that. Endurance is a 22 kilometre race over the endurance track, usually about between 20 and 23 laps depending on the length of the autocross track, and again fastest car to do that. On top of the endurance event is efficiency. So upon arriving at the competition and prior to technical inspection, you must insert an energy meter in line with your tractive system, which then monitors the energy you use throughout the endurance event. You're then judged on this. So UCM stands for the University of Canterbury Motorsport Team. As mentioned before, we're an engineering group that design, build and race single-seat race cars from the ground up each year. And we've been doing this for a wee while now. Unfortunately, Paul's not here to see my joke, but when he sees UCM, he probably sees it a bit more like that. So yeah, as I mentioned before, we established in 2013 with our first combustion car here on the left. By 2015, we'd climbed to 3rd in the internal combustion class in the world rankings. So we're still talking out of 600 universities. Though that 600 is split between internal combustion and... Sorry, 600 includes internal combustion and electric. So we wanted a bit more of a challenge, so 2016 came the idea that we would build our first electric vehicle. By the end of that year, we were the #1 electric vehicle team in the world for a rookie, so that means first year. By the end of 2018, we now sit at 25th in the world rankings out of about 120. So just a minute overview of some of the things I'm going to cover in my talk today. Our electric vehicles feature a 4-wheel drive topology where we have 4 independently controlled permanent magnet synchronous motors. The combined powertrain gives us 120 kilowatts. An 8.6 kilowatt hour lithium ion battery pack, multiple CAN bus communication networks, a vehicle control unit featuring a Cortex M4 processor, and a network of analog and discrete fault sense and vehicle shutdown systems. So just on here, the accumulator puts out DC, is then put into the quad inverter package. So there's actually 4 inverters mounted in here, which then control each of the motors separately. And then the control unit is supervising it all with a network of the analog devices, which are responsible for shutting down the card independently of programmable logic. So to drive a car, you must have a drivetrain. As a first year team, you must decide what path you want to go down, whether you want to go for a single motor or a 4-wheel drive topology. The single motor is inherently much simpler than any of the other topologies, and you can almost hot swap it for a combustion engine chassis. On the other hand, a 4-wheel drive car offers much higher performance advantages. Some of these include, for example, a car gets its tractive motion from the reaction force between a driven tyre and the ground. Similarly, for cornering, it's that same reaction force but in a lateral direction. With a 4-wheel drive car, you can develop control systems that can independently control those wheels to maximise that reaction force at any one time. Also, for when braking, the load transfer to the front wheels means that you're able to regenerate a lot more energy than with a 4-wheel drive topology than what you could with a rear-wheel drive car. Given the performance advantages with a 4-wheel drive topology, we decided that this is the direction that UCM wanted to go down, despite the significant added complexity with doing this. As mentioned prior, we also feature a custom-designed planetary gearbox that mounts on the end of the motor shaft as well. So there are essentially about 3 different main ways to go down if you choose a 4-wheel drive topology. The first one is to buy a well-established package that is quite popular with the top SAE teams. The second one is to use this package from AMK, or sorry, use the motors from AMK and develop your own inverter. Or if you're really ambitious like some teams, design, build your own motors and inverter. As a first year team or a new team, we didn't want to go down or take too much of a bite, so we bought the four-wheel drive Formula Student package from AMK Germany. It features again a quad inverter package mounted to an aluminium cooling plate, and each motor connects to it with the 3 phases and an encoder line. It is controlled using CAN bus and requires a control unit to send it the control messages. So this is the inverter once packaged for our cars. It's just in an aluminium housing with the DC in and then the AC output on the side there. These are control connectors, and this is the 35 kilowatt peak permanent magnet motor. Then an electric car, of course, cannot drive without its energy source. This is a bit of a block diagram of our accumulator. So we have a big series chain of lithium-ion cells, and they're separated into modules. Now this is to satisfy a rule in the rule book that governs how big a single module can be based on its peak voltage and energy storage. So for our 2018 accumulator, we had 10 modules, seen here, and they are all daisy-chained together using maintenance connectors. The system then goes through a tractive fuse, through isolation relays, and then to the output connector. This part here is called the pre-charge system, and that is needed because the high intermediate capacitor on the inverter, that would draw a high surge current if the pack was directly connected to it. So we pre-charge using a big power resistor. The control for this is done via our battery management system upon a request over CAN from the vehicle control unit. I'll go into a bit later, but everything is galvanically isolated between the tractive system and the connection to the rest of the car. One of the biggest points of design when designing a battery is your accumulator cells. This basically governs everything from the size, weight and energy capacity. So some of the considerations that we make are of course the energy requirement, the total weight of the pack, the cost, the temperature rise that you expect during simulations, the physical size and ease of assembly. These are the 3 most popular cell choices for Formula Student teams. In our first year we went for a single lithium ion cell which was spot welded to form the pack, but due to reliability and the significant complexity with this pack, we then went to a pre-packaged lithium ion brick, seen here, which we buy from Lithuania, and these all just bolt in series with bus bars, which is much simpler. It also has a 4-point thermocouple built in that we can tap into with a custom temperature monitoring system to give us accurate monitoring of that. The other really popular solution with some of the top teams is the Melasta LiPo pouch cell. Typically LiPos offer or allow you to have a much lighter accumulator, because with Formula SAE the ratio between high power and high energy favours that of the LiPo, which has higher power density rather than high energy density. Lithium ion has a higher energy density compared to its power ratings. So typically to get the power you need more lithium ion. But of course with this one, it's a lot harder to package than with the lithium ion bricks. So we just went for that simple option, which is of course safe with such a small electrical team that we have. This is a little snapshot of the front end of the 2018 accumulator. So here we have the isolation relays, the tractive fuse and the output connector. These are individual modules which are connected together in series with the maintenance connectors, which you can see one here, and they just connect through all these red tabs. The white wires coming out are the taps into the tops of the cells for the temperature monitoring, in which a student designed board will go into, or will form the temperature monitoring network. All the communication through the accumulator is done via CAN bus. Down the side we have the pre-charge system and also a few other safety electronics for detecting high voltage and being able to, well basically there's a light that sits up here and is illuminated when the tractive voltage at the terminals is over 60 volts, as well as monitoring the temperature of that pre-charge system. The biggest safety part of the accumulator is the battery management system. So we use a distributed battery management system, and the advantage of that is it means we can distribute the heat generated from our balance currents. So on top of each brick is a cell balancing board, and they're all daisy chained together to form a single module, and a communication wire which taps into the most negative and the most positive of each module feeds back to the central unit, in which the balance algorithms as well as the charge current algorithms are controlled. The contactor control and communication with the rest of the car is done via CAN bus through that connector, and the relay controls are done from here as well. As mentioned before, everything inside the tractive system must be galvanically isolated from anything low voltage. So, in order to do this, we have a accumulator isolation board which forms the part of our battery management system. We have a supervising microcontroller, and all the communication to the accumulator is done via opto transistors and CAN transceivers, as well as isolated DC-DC converters. The charger, we buy an off-the-shelf charger, but we add a few of our own circuits to conform to rules compliance. Some of these include insulation monitoring and fault latching, as well as some CAN control to tell the charger what to do via these buttons. And then all the USB interfaces have to be opto-isolated. The brains of the car, the vehicle control unit. The vehicle control unit reads all sensors and writes data to be logged via CAN. All the sensors in the car are via CAN bus. We have no analog signals running. That's done by a custom designed PCB that basically converts the analog signals to CAN at the sensor. It calculates motor torque requests from driver inputs and therefore controls the inverter. Controls auxiliaries, runs the pumps and fans, and the low voltage power distribution module. It does plausibility checks between the state of the vehicle and what the driver is actually requesting, as well as controlling the high voltage contactors. Deep inside that Cortex M4 processor is what is the most theoretically and complex part of the electric vehicle, and that's our dynamics, our vehicle dynamic algorithms. To date, we have implemented probably the most simple form of vehicle dynamics that you can with a four-wheel drive car, and that's basically just an electronic differential. So during cornering, based on the steering angle, we can change the torque requested to each motor. So that's going between the inside and outside wheels, and that allows us to corner faster, changing that reaction force. There's a fixed front-rear bias to account for the load transfer during acceleration. Traction control algorithm limits the wheel velocities to within an expected range, so that we can stop wheel slip. There's an inherent difficulty with traction control in four-wheel drive cars because without the complex controls that I'll sort of mention in a second, it's really hard to tell what wheel is actually slipping. So we are only at the very start of torque vectoring, and to get more in depth we need to overcome some of these big challenges. One of these is Kalman filtering of the inertial measurement unit encoders and GPS signal to find an accurate vehicle velocity and yaw rate in real time. Implement a high accuracy GPS, as well as implementation of vehicle and tyre models to calculate a desired yaw rate, which is then used to find required torques for each wheel. This is a really complex control system and modelling project, which we haven't had someone to really dive into quite yet, but it is in the works at the moment. Safety systems. About 80% of this vehicle, the electronics in this vehicle are just for safety. Some of the main ones are the insulation monitoring between high voltage and the grounded low voltage system, and this is done by a off-the-shelf PCB which inserts a high frequency signal onto the DC, high voltage DC, and if it detects any of that frequency on the low voltage ground, then it will output a fault which shuts down the car. We monitor the temperature of those pre-charge and discharge components and do plausibility checks between tractive power and actual driver commands. In the accumulator, we have, of course, the battery management system monitoring cell voltages as well as the custom temperature monitoring. We have power limiting software and the shutdown circuit. The shutdown circuit is a single line that runs the length of the car. or a whole loop around the car, and it has 27 switches on it. If any one of these switches breaks, the contactors may lose their power. And all these switches, well, some of them include the faults that I talked about before, like insulation monitoring and the pre-charge temperature, as well as things like e-stops, high voltage connector interlocks, and the inertia switch, which trips if the car's in a crash. Before making it to competition and even getting to technical inspection, we must prove that our car will pass the rules by design. So this is done with a 104-page document that details every wire, high voltage component rating, fault detection circuit and driver signal algorithm in the vehicle. It's complemented with the 106 element failure mode analysis form, which is essentially a list of every possible thing that could go wrong with the car and the mechanisms that we've put in place to deal with that. So we've built these fantastic looking cars, so how did we go? UCM 16 was first built on course in 2016 by electrical master's student Matt Barham and first drove in September 2016. At the Australasia competition, it became the first electric vehicle to ever win a dynamic event in the history of the competition, and that was in the skid pan. It came second in business, third in design and 12th overall. Unfortunately, this car suffered from some temperature issues as well as a mechanical failure on one of the wheel assemblies, so it wasn't able to finish endurance. UCM 18E was a redeveloped 2016 system with an entirely new accumulator. Electrical systems by myself and an electrical FYP team. It had focus on reliability and first drove in August 2018, just outside the mechanical wing. At the competition, we took out first place in business, second place in endurance, third autocross and fourth overall. We're also the first Australasian built four-wheel drive electric vehicle to ever finish the endurance event in the history of the competition. We would have been the first ever, but unfortunately we're beaten by 30 minutes by this seven-figure monster from Germany. With sponsorship from Panasonic and Audi, it had the nickname the Grim Reaper. 2019 and beyond. So this year, there's an entirely reworked electrical system with different accumulator cells, major mechanical changes, as well as the development in the vehicle dynamics. Unfortunately, I can't go into too much detail until the official unveil, but these are some of the things we're working on. I think you can probably expect to see a reasonably different looking car to what you've seen previously, which is quite exciting. Future work. So I'd love to see some advanced torque vectoring and traction control work done, as well as a self-developed silicon carbide inverter for increase the air efficiency and of course decrease the size. A custom BMS would be required as well, as talks about a driverless vehicle. The driverless competition has been running in Germany for a number of years, and there's been a bit of interest being picked up in Australasia now. Essentially, these cars operate exactly as a normal SAE car or former student car, in which a driver can jump in and drive them, but they also have the features required to drive autonomously, in which they do on the same style track. To do this is pretty complex, so UCM really needs more ECE, FYPs and postgrads. So if any academics here could see a potential project opportunity, I'm sure UCM would love to hear about it. So for the last couple of years, UCM's been at the forefront of this university's electric vehicle development program and showcasing it to the world. So thank you very much for taking your time for listening, and I hope I've stimulated a bit of interest in what we do. I'm also aware that not everyone here has probably actually seen the car drive, so I've chucked in a wee video of the car. This was when we first arrived in Australia at the end of last year, and this was our first shakedown after we took it off the plane. We had to take the front wing off because this dip here in the netball courts kept scraping it. This was also running 2/3 power because we didn't want to cook anything on our first day. Sweet. So, thanks very much for listening. We got any questions?
Audi are owned by VW, aren't they? How do you check the software in that Audi car? They probably cheat.
I don't think they'd. I don't think they'd let us close to that.
So, on the drivers, so what do you think about the factors for drivers in this competition?
Like whether I think it's possible.
I mean, the whole percentage, like in the result, like contributions to the competition result, the driver.
The driver's ability.
Yeah.
Actually, quite a lot. So, at the higher end, all the cars are performing quite well, obviously. So, it really does come down to the drivers who have had the most seat time, which comes back to the team getting the car finished and having things like ergonomic considerations made. So, yeah, there's actually a lot of points allocated to a driver's skill in the end. Fortunately, UCM has attracted some quite talented drivers in the past, so we've always had really good skills in our seats.
So student.
Yep, they're all students and they have to be engineers on the team. They're first selected, we go out to the kart track and have a bit of a race round and then take the top 10, and then usually we take them out in one of our previous cars and run them through some of the events to see how they handle it. And then from that we decrease the size of the team with selecting the main team plus some reserves, and then once the car's built, it's real hard into training them with that.
You mentioned there's like major mechanical changes in the next iteration of the cars.
Yep.
What would you expect?
New gearbox topology, new aerodynamics, new chassis new chassis materials that we haven't used in electric vehicles before. New suspension setup, so the suspension that they're using hasn't been used before in the team. So yeah, pretty different looking.
What's the aerodynamics? Is it the under tray and stuff like that?
Yeah.
Do you have any issues with your pre-race checks that you need to go through and stuff?
Like at the competition?
Yeah.
Yep, so we actually had a pretty major problem when we got to the competition. During unloading the car, we accidentally damaged one of our PCBs, and which basically meant, I knew that we wouldn't pass technical inspection with it in its current state. So we converted our camper van into a surface mount lab that night, and we worked on it until very, very early hours, and we got it done and made it through tech inspection. Unfortunately, that did actually mean that we weren't able to make it to the acceleration event because we were still getting through tech inspection. So that did cost us the points that we needed to get a third place on the podium. But I mean, these things happen. It was just unforeseen, and the fact that we were able to recover from it, I reckon, was pretty awesome.
Is it the skid pan?
Our first event was the skid pan. We missed out on acceleration, and it's kind of a shame because we would have done really well on it.
Yeah, like placings changed quite a bit between you were first in the skid pan for 2016 and then that wasn't one of your features in 2018. Is that like a compromise where you were going for reliability, or is it just like something?
That essentially it just came down to the driver. We didn't give our drivers enough seat time last year. We had issues with getting the car out. A few failures with our electrical system that required a lot of time for the car to be hung up and us fixing them.
Yeah.
Whereas the previous year for the skid pan event, they had a really well-trained driver, and he was able to go out and really nail it. Where we had quite an experienced team. It comes back to the whole team, and we just didn't have the seat time to do well in skid pan. However, we did have really skilled drivers for autocross and endurance, which we got our points back.
So Thomas, when you do that emergency disconnect, what happens? Does it just coast? If the car was running, it isolates the battery.
Yeah.
Does that mean for the rest of the vehicle it just coasts to a standstill at some stage? Or?
Yeah. So if that safety line's tripped, the contactors lose their power, and so there's nothing at the terminals of the battery, and then the inverter loses its power and the car will just stop. So since there's no...
So but it doesn't literally break?
No, it won't be able to break because the DC line's broken, so it'll just coast.
Do you have a combination of regenerative brakes and normal brakes, or just normal brakes, or just regenerative brakes? Or what's
You have to have a combination of both.
right.
Yeah.
So in that case, then your regenerative won't work, but your normal brakes will, you can both.
Yeah. There's rules about how much percentage of pedal travel you can allow before mechanical brakes kick in. Sort of thing.
How does the performance versus efficiency competition work? I mean, if you drive slower, I guess you might be more efficient, but lose on the performance side. Is there like a...
Yeah, it's a little bit of trade. Well, efficiency is significantly less points. So ultimately, you're designed for speed, but with efficiency in mind. Our cars, or the 2018 car, was actually really inefficient because of the gearboxes. We used a single stage, which is simpler but is less efficient. So yeah, we lost quite a few points in efficiency, but yeah, for us, I think it's usually the top teams. Once you've got a well-established car, that's when you start optimising for efficiency, like dropping weight off where possible and that sort of thing. But for teams who are just starting out, it's more about getting a reliable car that can finish endurance, and if you get time, you can start making those efficiency considerations. One of the big ones for electric cars is, of course, optimising regen braking. So making sure your algorithms that run that are maximising the amount of current you can get back at any one time.
I have a question. Hello? You have this thing?
You said on one of your slides you're going to put in a high accuracy GPS. What's the purpose of that?
To aid the vehicle aid the traction control and torque vectoring algorithm. So basically, you run it through the Kalman filter and be able to generate an accurate actual vehicle velocity.
Okay. What kind of improvements, like, do you think you'll see there, torque vector?
You'd see much higher efficiency and basic performance as well, because it can turn faster.
Can that compare to an IMU? Is an IMU just compared to that, or is it GPS?
You'd use the GPS I think they use it as a correction for the IMU to stop. Yeah, or other way around. I'm not an expert on it myself, but yeah, that's why they run it through the filter to use the both of them rather than just one. At the moment we just have an IMU, so you can get a bit of drift with them, which is hard to deal with.
Because is it quite hard to get such an accurate GPS?
Yeah, unless you've got big money.
Yeah, yeah.
Given that readings are so important, do you think that there's any viability in like a front-wheel drive design? If you had to go for a two-wheel drive plug-in, do you think you consider that?
Nah, I think because efficiency is only 100 points out of the, I don't know what the combined total of all the other dynamic events are. I think you'd lose out a lot more on, your cornering ability and acceleration ability and all three other events that would significantly dominate the advantage you'd get with having it in efficiency. I think with having four-wheel drive, the difference between having a four-wheel drive and a two-wheel drive front-wheel car, I don't think that would be such a big trade-off, because you've already got the complexity of having to have in-wheel motors, cables run to your front motors, and like having motors on your turning wheels is one of the most complex part. So I think if you're already having a front-wheel drive car, you've sort of had to overcome some of the biggest challenges you'd face anyway. The only thing you would say would potentially be weight on the rear, but again, you'd make that up with power, considering like these 35 kilowatt motors are only 4 kilos or 3.5 kilo.
I'm just interested in the dead reckoning. And how would you propose to measure the wheel slip? You would be using the dead reckoning.
Yeah.
The better the wheel slip, obviously the better the dead reckoning.
Yeah. The wheel slip is measured with a sensor that is so expensive that most teams actually just hire it. And that's 20,000 euros for a season. And so, yeah. It's,
but developing your own, what would you do?
I have no idea. Yeah.
I mean, you'd have RPM, obviously.
Yeah, we've got RPM from the encoder.
So that would take you a long way, wouldn't it?
Yeah. But I guess the thing is, being able to detect slip.
Speed over the track as well, so you usually put a laser down or a light down onto the track. You combine that with the wheel speed, with the RPM to get you that slip.
So don't anti-blocking systems. Doesn't ABS continuously track the slips?
Yeah, that's
So those sensors are so expensive.
Yeah.
Because you wouldn't be able to have ABS in your car if it was 20
No.
grand per sensor.
No.
Could you do it with the GPS side and your combination compared to your encoders, or is that not how it works?
Yeah, I think it's. Again, I'm not an expert on this. I hadn't had an opportunity to get into it. Actually, I joined the team 4 years ago to learn about it, and I just ended up building cars and getting them to a point where they can take a traction control algorithm and not being able to actually implement it.
Often the GPS is just used to tell which corner you're at, so you can turn the traction control up and down depending on what sort of corner you're at.
Okay.
They're not sort of, yeah.
Because is the slip not just how fast your car's going, how fast the wheels are moving, or I don't know anything about it.
Yeah, I would love to have answers to this question.
You want some slip because the tyre traction is a little bit better if the wheels slip.
Yeah, 6%, I think.
Can you actually learn the track? Can you? So if you know if you've got an accurate position, you know this part of the track, therefore you can have an optimal tuning of the vehicle.
Well, maybe. I suppose probably go down the driverless course.
Oh, yeah, the driverless.
Yeah.
Just adjust what the driver's doing, it's like calling it.
I don't reckon you ever be the driver. Yeah, interesting.
Yeah.
Autonomous versus a driver.
Yeah, well, they're doing it now. By 2022, the Formula Student Germany competition require all cars that enter to be able to do the acceleration event completely driverless. And then after that, the skip band event must be done completely driverless.
That's not because they're reaching a physiological level of what a driver can actually deal with?
No,
In
just
terms of acceleration?
no. Well, you'll get a much higher acceleration with no driver in it because of low weight, but yeah, they're just trying to push the technology there.
People are not going unconscious quite yet.
I mean, hard to get to 11G with it.
Yeah, not quite.
You didn't have a supersonic speeds to get to 11G with it.
Yeah, I'd say we need bigger motors than what we've got now, and some
Sorry, last point that I had, what I wanted to ask was that, so my countryman rocking up with what is basically an Audi race car, does that mean there's no limit to funding in the competition? Is there a limit there? I've never thought about it.
Yeah, well, every team's responsible for funding their own car.
So there's basically no upper limit. There's no thing that the team can spend this much, because that means that the competition is really skewed in a way. So well done, actually.
Yeah, and I think that's probably quite a testament to the University of Canterbury, where we don't have the big budgets.
So there should be a cost competition category where you win for the cheapest car, best competition, actually.
What would be the performance difference between this car and a Formula E car?
Not entirely sure, but I've seen some reports done of some of the top Swiss teams. Their cars turn like corner faster than a Formula E car, but they just get taken out in the straights. So yeah, on a tight track, these cars are faster.
They're twice the power, aren't they? They're 200 kilowatts Formula E.
Yeah, something like that.
Do you find you're limited with any of your pre-packaged components or modules that you bought? Do you find you were limited in any way?
In what way?
Like, say you had to make compromises to work around some kind of configuration that you control the unit or your battery.
Oh yeah. I spent a good part of my life going through issues with off-the-shelf components and making them rules compliant and working in that vehicle. Yep, I've got grey hairs out the back of my head because of it.
You talked about some of the first car sort of thermal issues and stuff like that. Do you encounter any problems in the future? How do you kind of rectify that and control it? Did you ever have to find yourself like, degrading performance because
Yeah, we use a combination of all those things. So the first car had a single cooling loop that ran through the motors and inverters, but the motors work at an operating temperature much higher than what the inverter can. So that was rectified by splitting the two cooling loops. We also implement a derating function in the control unit, which is basically we can write a curve, a derate curve, and so where the inverter is sitting in its temperature, we'll just apply a multiplier less than 1 to the torques in the vehicle, essentially.
Did you find that was happening much? Like once you split out the two cooling loops, was that going to get like? Do you know if it got used? Like if it did derate once you split two cooling loops?
No. With the cooling loops separated and the fans running, it won't derate. But yeah, if there's been a couple of times I've seen the car out and forgot to push the pumps and fans button, it derates, within 10 minutes. Because without that, it definitely does need the cooling, and the problem was solved by splitting it.
Yeah, I was to say, this incredible work that Thomas has done. It's just pretty unbelievable. It's putting us where we are. Yeah, so it's some awesome. Thanks a lot, Thomas. Brilliant.
All right.